Hello and welcome to Module 4. In this module, we're going to be taking a closer look at the basic architecture of the Hadoop Distributed File System, or HDFS. So the data that we are going to be putting into our big data environment is going to be residing within the Hadoop file structure. And this Hadoop Distributed File System is designed to optimize the process of basically spreading data out under multiple nodes so that we can take advantage of horizontal clustering. And that gives us the ability to process larger amounts of data that's coming at us maybe at a faster rate at a more efficient speed. So let's start by taking a little look at some housekeeping issues, and then we'll move into Module 4 on basic cluster architecture. A couple of quick housekeeping issues before we get started. Based on the performance on the last assignment, I just wanted to make sure that we're clear on a couple of things because this is kind of important from this point going forward. To start with, as a reminder, remember that I do not accept late work, so I don't take late assignments in my graduate classes. So it's very important that you try to get those assignments submitted on time. I am more than happy to handle questions as they come in. Like I mentioned earlier, the more information that you can give me about your situation, the easier I'm going to be able to help you. So, come prepared basically and present as much data as you can about the context of your question. It's going to be a bit easier for me to handle the situation. As some of you have discovered, as you've gone through this last session, I have limited Mac experience. I know Linux very well, but Mac is something I'm not quite as familiar with. So bear with me on if you've got Macintosh issues. That's not a system that I use on a regular basis. I should be able to help you on Linux issues, should be able to help you just fine on the Windows platform issues. So I just kind of bear that in mind. Also, I highly recommend that you start on assignments earlier than later, because if you do run into technical issues, it's pretty important that you get those questions to me sooner than later so that I can try to address your issues as fast as I can. Okay. Also, I did want to mention that now that we've got everything kind of finalized in place with regard to those students on the research path, I think those have definitely identified themselves. Then we're ready to go ahead and move forward into organizing the project groups. So I'm going to be providing more information about this a little bit later this week, but I will organize project groups and then I'll provide more information about that either later this week or early next week. I also wanted to put out a couple of reminders about the AWS sandbox behavior because there's still questions coming in on this. So if you watch the video for Module 3, I walked you through the process of how to go about cloning a virtual cluster, so cloning that EMR cluster whenever you needed to kind of restart your work again. So a couple of behaviors that you're going to notice, just make you aware. Essentially, the work that you do within the sandbox in general, in terms of like configuring AWS or things like that, that sticks, right? So every single time that you go in there, you'll see all the previous EMR clusters you had. That isn't deleted. You have the ability to clone an existing cluster. None of that information has gone. However, the actual AWS artifacts themselves, so the clusters that we start up, maybe the interaction that we have with Linux, the files that we copy over, things like that, those are all wiped out when we terminate the sandbox. So just kind of be aware of this. Now, with that in mind, I'm actually being very careful to make sure that the exercises that we do don't assume that you've completed prior exercises and stored that state. So I'll give you everything that you need to start each exercise, including files you'll need to start and things like that. So just kind of be aware that that stuff's going to get wiped out. So make sure that when you're ready to start working on your homework assignments, you just bear that in mind. You've got basically a 4-hour chunk of time that the sandbox is alive, and then you have that time to work uninterrupted inside that cluster. Be aware that if there's a 1-hour idle time, that cluster will be terminated if you don't work on it. Even if the sandbox is still running, that cluster will be terminated after a 1-hour idle time, and that will unfortunately destroy your work. And also when you terminate it, or if you just terminate the sandbox without terminating the cluster, that will also terminate it as well. So just kind of be aware of all of this. If you need a reminder on how to go about cloning a cluster and connecting to it using your SSH client, then go back and revisit the module 3 video that I did that describes that process, and that should clear that up for you. So just kind of work that into your recipe, if you will, in terms of your timing and things like that, just so that you're aware of how that behavior works. So again, I've still been getting a lot of questions. Hey, this seems weird. Is this expected? I probably should point out that this weird behavior, this auto terminate behavior and so forth, is all because AWS is trying to preserve your budget, right? So they've given us the sandbox environment with a very limited budget, and that limited budget obviously is going to get chewed up really quickly if we just leave services running all the time and so forth. So just that's basically why it's done this way. So they're giving us free resources to work on it, and so we have to play by their rules. Now, the good news is if you had an AWS account, you were willing to pay for the services out of your own pocket, you could certainly set up your own AWS account, your own clusters, leave them running, and all that kind of good stuff. So that's an option. But the whole point of having the sandbox is that you don't have to pay any money out of pocket in order to learn these tools and work with these services. So I realize some of it's a little bit of a pain, but that's how we're going to attack it. The last thing that I want to talk about is the relationship between Linux and Hadoop, because there were some questions on this as well this week. And I noticed some confusion as I was going through the assignments. So what's important to understand is that Linux and Hadoop each basically have their own file system. They are their own operating system. So Linux is essentially the host for the Hadoop distributed file system. Hadoop is going to be running on Linux in our environment. Okay. Now we can go ahead and create files and directories and users and control permissions in Linux, right? That is basically the host system. However, Hadoop has its own file system as well. So you can also go into Hadoop and create files and folders, directories, users, and so forth. So as you saw in your assignment, you can basically do this at either level. It's important to understand the difference in what's happening at each level. So for the most part, when we're talking about working with distributed processing, the distributed file system, we're talking about working at the Hadoop layer. You create a file within Hadoop, then it's up to Hadoop to keep track of where all of these file structures are located and so forth. That's not Linux's job per se. So Linux basically is just the workhorse at that point, providing the actual services to read and write and so forth, but it's all being managed, directed by Hadoop. So in other words, if you create a user in Linux, you won't see that user in Hadoop. You create a file in Linux, you won't see that file in Hadoop. Okay, so if you have something running in Hadoop, also you create a file in Hadoop, you're not going to see it on the Linux side. So kind of think of these as two separate operating systems. They very much are separate operating systems. It's just that Linux is essentially acting as the host for Hadoop. So Linux is responsible for physically handling all the exchange of information to from the hardware and so forth. That's basically the layer that takes care of all of that essential activity. Okay, so hopefully that clarifies what's happening here, because I got numerous questions as, hey, we're doing the same thing here, we're doing over there. I'm very confused. I don't understand what's going on. Well, that's the nuts and bolts of it. Okay, so most of what we're going to be doing is working on the Hadoop side, but basic Linux commands, things like that, are also useful because occasionally we have to use Linux to Hadoop to tune the Hadoop system and so forth. Okay. So do remember that the assignments are going to be due on Sunday night. I'm going to be posting these videos on Monday. I decided to do that. I realize you lose a day kind of on the video, but the advantage is it gives me the opportunity to review your work and be able to address any issues that I see in the videos. So I'm probably going to be continuing to do that through the remainder of the semester, just posting these videos on Mondays. Okay, if you have any questions on the assignments, let me know. Again, remember they're 10 points each, 10 points each, and if you miss an assignment, you lose those 10 points. There's no way to get those back. So stay on top of your work and let me know if you've got any questions or problems. To continue, let's discuss the chapter objectives for this Module 4. The first thing we're going to do is spend a little bit of time looking at the difference between traditional data storage and Hadoop. We'll also take a look at the basic structure of HDFS, the Hadoop Distributed File System, and also to be able to articulate basic capacity metrics for HDFS, how to calculate them, understand them, and so forth. And do be aware that HDFS, as part of the Hadoop Distributed File System, is one of those core elements of Hadoop. So every Hadoop version or installation comes with the Hadoop Distributed File System. We're using EMR, which stands for Elastic MapReduce, and that's actually the Amazon or AWS implementation of Hadoop. So it's its own flavor. There are obviously a variety of different flavors of Hadoop out there. So this is the particular flavor that we're using, is the one that's included with AWS. But the basic core and structure is pretty much all the same. And so HDFS is an important part of that. Let's begin by taking a closer look at the traditional architecture of a relational data environment and talk about how that compares with the more big data oriented storage of HDFS or the Hadoop storage. So in the traditional architecture, we have essentially a relational database management system is what I'm talking about in terms of traditional. So Oracle, SQL Server, tools like this. MySQL or MySQL. Those are the kinds of tools that I'm talking about when I talk about traditional architecture. So relational database management systems. Now, if you're familiar with relational database management systems, you've looked at like EF-COD's rules on normalization and how SQL basically works and so forth. You know the basic drill. So the whole idea is that we have data distributed across multiple tables, those tables joined together, and so forth. Most of the time in a relational database management system or a more traditional architecture, you have usually one processing server and one or more data repositories. Very often they all sit on the same machine. So if I install Microsoft SQL Server, for example, on my local computer, then I'm running the SQL service, I'm running the data services, everything basically on that machine. And that's very convenient because the way that the traditional architecture works, wherever the data happens to be sitting, you have to move the data to wherever the processing is taking place so that it can run through those processes. So in this particular case, SQL queries, for example. And then you can get your output. So that's actually what's being illustrated here. If you take a look at the diagram, you'll notice that you've got step one, so we issue a SQL statement. That will, in the SQL statement, identify the specific data elements we're going to need. So basically you have your from clause that tells us which tables we need data from. We're going to have to go to the various data nodes. And if they're all sitting on the same server, that's really convenient, right? Then I don't have to move data across the network in order to get that. But basically you have to go get the data. You bring the data to wherever the process is physically executing. That will execute the process and get you those results. And so that's the standard way that this works. Now, again, I did mention that we usually have one processing server, although it is possible to cluster those processing servers. So if we have more than one processing server, the idea is that these two servers are basically running in parallel, and then we're going to have some sort of network connection to establish a heartbeat between these two servers. And one or the other is going to be handling the processing, but it also makes sure that the other server is aware of what's going on and so forth. This kind of model is kind of useful if you want to do a hot fail-safe. If one of those machines goes down, you've got redundancy, that sort of thing. So it can get a little expensive and a little complicated, but it's basically just multiple processing servers that are all responsible for running code. But either way, you've got to move the data to those particular servers in order to process the data. So the data nodes, again, they could be on the same machine or they could be distributed across multiple other machines. You may actually have a completely separate bank of hard drives where all of the data is physically stored, but you still have to go through that process of moving that data from those data nodes, from those data repositories to your processing servers before they can actually process the data and we get the results. So you see the potential problems here, because if I'm going to have to move the data to the server before I can actually do processing, that means there's some elements of processing such as filtering, like through a where clause in SQL Server, or aggregating or things like that, that are going to have to be done after the data is physically pulled up. So am I going to be moving more data to the processing server than I really need? Well, it's very likely that we could be doing that, right? So there's some inefficiencies there in the system. There are also issues with this particular approach in that all the services are basically running, the processing is running on a single machine, which means that if we run out of resources, such as memory, for example, that can slow everything down. And I can throw more memory at that processing server to increase its capacity. This is scaling, it's vertical scaling, because I'm basically just continue to throw more and more resources at that box, hoping that I can improve that performance. But there's going to be a point that I'm going to hit a cap. I'm going to hit a limit, either based on budget or maybe even based on the architecture of the operating system I'm using or something like that. There's only so far you can go when you try to scale up in this way. So this particular issue is why a new architecture is needed for big data. So the alternative, instead of using a traditional architecture like this, is to use a distributed file system architecture. So the HDFS architecture looks something like this. So in the HDFS architecture, when we use the term node, just so you know, each node is basically a machine. So that could either be a physical machine or it could be a virtual machine as well, depending on how we put it together. Most cloud-based services, everything is done with virtual machines as opposed to physical machines. Although most cloud services, if you want to pay extra to have physical machines, you can certainly do that and have dedicated machines. But for the most part, they're generally going to be virtual machines. So each node is a machine, and there are a couple of different kinds of nodes in HDFS. We have what's called a name node, and the name node is basically where all the metadata is stored. So it stores essentially a file image, and so it knows where all the file structures and everything are stored everywhere within the various data nodes, and it knows how those things are split up and how all their allocations are made and so forth. So essentially, when a client needs to get access to resources, it goes to the name node. When we connect to a cluster, we generally connect to the name node, and that name node identifies the locations of the various pieces of data that we need, and then we'll tell the client what we need and then allow the client to actually pull data directly from those processing nodes, or those data nodes. Now, the name node is basically, again, going to keep heartbeats going with all the various data nodes. So each rack contains a bunch of servers. It'll contain heartbeats to those servers, so it knows if they're up or down. Also notice that we have a secondary name node. That's for redundancy reasons. So if something were to happen in the name node, the secondary name node can be promoted in its place. That way, if the name node goes down, my whole cluster isn't accessible. The other big difference in this model is that we're actually pushing our processing requests down to those data nodes. So even though the name node knows where everything is located, it's not responsible for the physical processing. So that's something a little different from the traditional model where you've got a single processing server and then it pulls data from various locations. You'll notice what's actually happening is the client is pushing requests down to each of these various data node structures. And part of that is actually going to be the processing request. So in other words, what's happening here is that instead of having the data get migrated back to wherever the processing takes place, like we see in a traditional model with an HDFS or a distributed file system architecture, we do it the other way around. We're actually going to be pushing the processing request down to where the data is, which makes more sense. Then we allow those little snippets of processing activity that are relevant for those data nodes to happen at the location, and then results are simply passed back and processed. Okay, this is actually what MapReduce is all about. So when we get into MapReduce here in the next week, we're going to learn much more about how all this process takes place. Now, I do want to point out here that the files themselves couldn't be distributed across multiple data nodes. So let's say I've got a file that's 500 gigabytes in size, and I want to store that in a distributed file system. I'm not going to store the whole thing on a single data node. I'm going to break that up into pieces. I'm going to distribute that across multiple data nodes. Generally, we'll have a segment within each rack, and then it's possible that we could have a piece of that then replicated to a data node in another rack and so forth for redundancy purposes. So those files can not only be distributed across multiple nodes, they can also be replicated across multiple nodes as well. So your book in chapter 3 goes into much more detail about this whole process and how it works. I just wanted to kind of walk through the logic of why it works this way, why we're doing it this way, and I think it makes sense when you consider it that way. Okay, so that's the basic HDFS architecture. Now, one of the advantages of HDFS is since that data is actually distributed, we have the potential of doing potentially distributed processing as well, which could be much more convenient. And even if we needed to read the entire data file for whatever reason, if it's distributed, that means that I could actually have multiple systems pushing data back to me at the same time. So let's take a look at a really simple example of how this may benefit us. So here's a potential situation we may run into. Let's say that we've got a file that's 500 gigabytes in size, okay? And that currently resides on a single computer. So let's say we're using a traditional approach, a standard relational database system. We've got a single machine, and the data happens to be sitting on the same, let's say the data is sitting on the same machine as the processor, but we still have to have the hard drive controller read that out and send that off to the processor. Okay, we're going to assume that there are 8 controllers, so we have 8 I/O channels, each of which can read data at 100 megabytes per second. How long does it take to read the entire file? Okay, so basically a simple question. If I had this 500 gigabyte file, how long would it take to literally extract or read the entire file, assuming everything is residing on the same computer? Well, basically, this is nothing more than a little mathematics, right? So we know that each gigabyte consists of 1024 megabytes, right? Therefore, 500 gigabytes equals 500 times 1024. So basically 512,000 megabytes in a 500 gigabyte block. Okay, so in other words, we're saying that our file that we want to read is 512 megabytes in size, 512,000 megabytes in size. Okay, now we're assuming that the read speed is 100 megabytes per second for each of those 8 I/O channels, each of those controllers. So 100 megabytes per second times 8 controllers equals 800 megabytes per second. Therefore, a little bit of math. If we've got 512 megabytes in the file and we divide that by 800 megabytes, that's the amount we can read in a second, then the whole thing will be finished reading in 640 seconds. In other words, 10.66 minutes. So it would take me 10 2/3 minutes to read a 500 gigabyte file on a single computer in this particular configuration. Okay, so if we were to break this up, if we were to take that file and distribute that across other machines and then have them all working together, so they're all reading simultaneously and they're pushing data back simultaneously, we could solve this situation, solve this problem much more quickly. Okay, so let's say that we wanted to build a cluster that had enough machines in it that we could read this file in 30 seconds or less. How many machines is it going to take to do that? Well, this calculation is pretty simple because if I know how long it takes one machine to do it, all we have to do is divide that by the target time, and that will tell us how many machines we need. So we know that we have 640 seconds of time to read that file on a single machine. We want the target time to be 30 seconds. So how many times does 30 go into 640? 21.3. So basically 22 computers. So 22 computers clustered together would allow us to resolve this read operation in 30 seconds or less, where it would have previously taken us 10.66 minutes. Okay, so that gives you just kind of a little example. Most of the mathematics around calculating capacity, things like that, are very similar, right? They're pretty straightforward, simply a matter of breaking it down into its component pieces and doing the calculation. Other things you may want to consider are also how to distribute the data across multiple nodes, how many depending on how many replications you have of each data node, how much more would that take? For example, this assumes that we don't have any replications, but we could certainly replicate this across multiple nodes, in which case we may have to increase our capacity a little bit more. So there's a lot involved here, but really the mathematics is usually pretty straightforward. Simply a matter of determining what your required resources are, and then dividing it by what's available, and then determining, basically solving for X, right? Either we're solving for the amount of time it will take, or solving for the number of machines that we need. So as long as you've got the sizes of the things you're working with, the speeds that you're working with, and your desired either desired number of machines or desired throughput times, then you should be able to calculate the last remaining element. Okay. So that's really all I wanted to talk about in this section. I think that your chapter 3, is going to cover this in a lot of detail. So read through that, especially the sections on the CAP theorem. The CAP theorem discusses kind of the rationale behind the Hadoop Distributed File System and how it differs from a relational database. Relational databases, because of the way that they're structured and architected, they give us a lot more data integrity options. But with distributed file systems, we pay a little bit of a price in terms of data integrity in order to get the pickup for performance. So CAP theorem will discuss that in more detail. And then the chapter will also go into more detail about how to do calculations for things like handling replicated data sets and so forth. So read that over, and then you should have the information that you need in order to do the assignment. So next, let's take a look at the assignment for this week. We're in chapter 3 of your big data book, so I'm going down to the bottom of that chapter to the list of practice exercises. I'm going to assign exercises 3-1 through 3-5. If you want to do 3-6, that's fine. Go ahead and move on. 3-6 is very similar to 3-5, so I only assigned 3-5. So all 5 problems were 2 points each, adding up to 10 points in the assignment. Each one is essentially going to have you calculate a time differential to explain how to go about organizing a replication model and so forth. So you shouldn't actually need to log on to your cluster at all to accomplish any of this. This is basically a paper and pencil exercise. But take a look at the practice exercises. Read through them once. My recommendation is read through the practice exercises once before you actually read the chapter. Then when you go back and read the chapter, you'll notice how the chapter will teach you essentially how all of these pieces fit together and how to do these various calculations and so forth. Okay, I did also mention the CAP theorem in the video. So this is the diagram of the CAP theorem, and basically what the CAP theorem tells us is that we have basically 2 of the 3 that we can use. We can never have all 3 in a distributed environment. So consistency, data consistency, availability, or partition tolerance. I can have, here's definitions of each of those if you need them. I can have 2 of the 3, but I can never have all 3. So when designing a distributed system, the CAP theorem says since you can only have 2 of the 3, decide which two are the most important for you and decide what it is you can sacrifice, and then leverage your system to make the most of the two things that you can use, and just basically work around that last one that you can't use. So the limitation, why we can't have all three, the reason we can't have all three is because we're not enforcing data integrity at the same level as we are in a relational database. In a relational database, yes, we do have all three, but we don't necessarily have partitions in relational databases in exactly the same way. And so it's this introduction of the partition and the provision of partition tolerance that really kind of introduces the kink in the model here. So I do spend a little bit of time with the CAP theorem that will help you better understand exactly why the databases or HDFS is structured the way that it is. All right, so the assignment for this week will be the practice exercises 3-1 through 3-5. If you have any questions or problems, let me know. Please go ahead and do these in a document and send them as a PDF file when you submit the lab assignment and or the homework assignment, and then I'll try to get those graded as quickly as possible once they're all turned in on Sunday. So that's all I've got for today. Thanks very much. Hope you had a good week, and let me know if you need any help with understanding the Hadoop Distributed File System and the difference between relational data structures and distributed file system structures.